Today, we from Group A1 will be conducting an experiment regarding buckling of strut. It will be a two-phase experiment using the TQR strut buckling apparatus, where one will include the usage of pin attachments and the other without. To begin with, regarding proper attire, in this experiment, we must wear a lab coat and safety shoes before beginning our experiment. Next, we must read the equipment procedure before using the equipment and handle the apparatus with care. Moving on, always pay attention during the briefing. The lab assistants will provide further insight into the experiment. Last but not least, we cannot eat, drink, or chew gum in the lab. For example, the consumption of this sweet beverage is not allowed. These are the apparatus that we will be using. This steel specimen of 1 meter in length will be the strut used to determine the buckling load for a fixed-ended strut and a pinned-ended strut. Next, these are the pin attachments that we will be installing at the load cells of the TQR strut buckling apparatus. They will be used during the second phase of the experiment. An Allen key will be used to screw the pin attachments in place. If these pin attachments are not screwed properly, they will move and fall out, compromising the experiment. We don't want that, do we? This small Allen key is the perfect size for the task. Introducing the TQR strut buckling apparatus, starting with the digital indicator displaying the load applied to the strut. Next is the screw jack, controlling the height of the load cell. The screw jack will be the main component that we will be manipulating throughout the experiment. This is the load cell. It has a counterpart that is supported by a beam and screw jacks. Up here, they hold the strut in place. Next, this is the displacement gauge, measuring the amount of mid-span deflection on the strut. Finally, these are the screw jacks that control the height of the load cell on top. We must balance them and lock them in place. Before starting the experiment, the digital indicator must be switched on and warmed up for 10 minutes. Ensuring accurate, stable reading by allowing internal components, especially sensors and circuits, to reach thermal equilibrium. Electronic components inside the digital indicator may experience slight fluctuations in performance due to the temperature change. Warming up allows these components to reach a stable operating temperature, reducing errors in measurement. Besides, initial power-up may cause zero drift, otherwise known as baseline drift, due to unstable electronics. Allowing warm-up helps the indicator stabilize at a true zero or a reference point, preventing inaccurate load readings. Measurement accuracy and repeatability improve after thermal stabilization. This is especially critical in buckling tests, where small displacements lead to large load variations and vice versa. Most high-precision digital indicators include warm-up recommendations in their manuals. This ensures users comply with calibration conditions and rated performance. Afterwards, we install the strut into the load cells. Then, the screw jacks on top will be turned, balanced, and then locked in place. Next, the bottom screw jack is turned clockwise to lock the strut in place. After ensuring the strut is snugly fit in the middle of the load cell, the tear button on the digital indicator is pressed to set the reading to 0. Following that, the bottom screw jack is turned clockwise until the digital indicator displays around 7.5 Newton before the tear button is pressed again. Finally, after ensuring the displacement gauge is at the mid-length of the strut, it is zeroed and the experiment is ready to begin. This experiment is divided into two phases. In the first phase, we investigate the buckling load of a fixed-ended strut, which is without the pin attachments here. In the second phase, pin attachments are connected to the load cells, allowing us to study the buckling load of a pin-ended strut. The pin attachment at the top load cell is screwed in place using the Allen key. To begin the experiment, the bottom screw jack is turned clockwise slowly to load the strut until a digital indicator displays the desired reading. Sudden application of load can lead to premature failure and damage to the specimen. Slow loading allows the structure to adjust to the load gradually, preventing sudden instability and allowing for a more controlled experiment. Then, the displacement gauge reading is taken. Both readings are then recorded and tabulated nicely. Since the applied load must always be less than 80% of the buckling load to prevent plastic deformation of the strut, after applying the maximum desired load to the strut, we turn the bottom screw jack counterclockwise to unload the strut to our next highest desired load. In this case, it is 120 Newton. There are two readings that are of interest to us in this experiment. The first reading is from the displacement gauge, which measures the amount of midspan deflection on the strut. To accurately obtain the reading, the outer dial of the displacement gauge is first read, followed by the inner dial, which records the number of complete revolutions of the outer dial. Each full revolution of the outer dial corresponds to an increment of 1 unit of the inner dial. To calculate the total deflection, combine the values from both dials and multiply the result by 0.01 mm, which is displacement value per division. We must take note that when the displacement gauge is zeroed prior to the start of the experiment, only the outer dial is affected. It means that the inner dial value is not zero if the strut is present. Here's a side-by-side comparison with the displacement gauge without the strut. Therefore, when interpreting the inner dial reading, the inner dial value during zeroing must subtract the obtained inner dial value to determine the actual number of revolutions that have occurred. This ensures an accurate measurement of the displacement from the original zero position. The second reading we must take note is from the digital indicator, which displays the amount of load applied to the strut in newtons. Both readings are then recorded and tabulated nicely. These are the dimensions of the strut, along with the calculated moment of inertia and theoretical buckling load with the given formula. Next, we present the experimental results for the first phase of the experiment, which investigates the buckling load for a fixed-ended strut. To improve accuracy and reliability, the average of 3 sets of deflection readings is taken to minimize random errors. A graph of deflection against deflection per unit load is plotted, where deflection is plotted on the y-axis and the deflection per unit load on the x-axis. The same table and graph format are used in the second phase of the experiment, which determines the buckling load for a pinned-ended strut. The maximum applied load in both experiments, 220 Newton, is less than 80% of buckling load, ensuring the strut remains in the elastic region. That is all from us, Group A1. Thank you for watching.